Hi, everyone. Welcome to Smart Sensors for Smarter Robots, improving robotic world understanding through Edge AI with Minhea Stoica from Zalmatech. Minhea is a hardware engineer with over 10 years of experience, the last 4 being focused on developing Edge AI-enabled products. As product manager at Zalmatech, he leads teams that develop hardware solutions across industrial, robotic, and medical verticals from initial concept through to market-ready products. Over to you, Minhea.
Okay, hello and thank you for having me. I'm super excited to be part of this event. So as David said, we are going to talk about smart sensors for smarter robots, right? So very short intro of the company I work for or with. I am part of Zalmatech, which is a company from Romania, which has a very cool offering of prototype to production hardware development services, mixed with its own line of products, which are basically a full-blown prototyping ecosystem used to hugely accelerate the services mentioned before. And in the next 15 minutes or so, I'll be arguing that if we want to build smarter and safer robots, we must help them better understand the world in which they function. And of course, I will be showing you how we intend to do that. So this is how it's going to happen. Firstly, we will talk about what world understanding really is and how we achieve it as humans. Afterwards, I will walk you through a very high-level overview of a modern robotic system and how it differs from a traditional robotic system and how they are actually built more like us and less like a robot that was built 25 years ago, trying to understand how AI fits in this new way of building robots. And afterwards, I will be walking you through what smart sensors are, this little guy, what they do exactly and how we build them. And then I will showcase 2 practical examples that we have already integrated in some projects, namely a smart nose and the smart tactile unit. So what is world understanding? If we are to be pedantic, it's a process by which a system, be it biological or artificial, perceives and interprets environmental data from multiple sensor inputs to create meaningful insights. So in simpler terms, it's basically a mechanism we've developed over millions and millions of years of evolution that allows us to interact safely and effectively with our environment. I'm not going to do a biology lecture, but I want to highlight that most of this interaction with the environment happens subconsciously. And this is largely due to 2 factors, which is information overload and speed. So think about it for a second. Imagine being constantly aware of maybe the temperature in your palms or the dryness of your eyes or every single ambient smell around you. And I feel like living in that heightened state of awareness would be not only very uncomfortable, but actually overwhelming. So our brain uses this little trick and filters out most of this to avoid cognitive overload. Think, for example, of the situation in which you hold a cup in your hand and talk with somebody. And if you were to divert your attention to holding the cup and make sure you don't drop the cup, you would not be able to hold a conversation. The brain automatically calculates how to grip the cup, how to adjust for its weight and maintain balance, and all of this without you needing to think about each step, and surely without diverting your attention from the conversation. Secondly, the subconscious processing of these sensory inputs actually help us react quickly to danger. So, for example, if you were to touch a hot mug, this causes us to immediately retract our hand, even before we consciously register what happened. And this is called a simple reflex arc, and it prioritizes speed without actually understanding that, oh, this mug may be a bit too hot for me to touch. Good, so this is how we do it. So now let's consider how robots might be achieving something similar to this. And to do that, we first need to understand how robots actually work in order to figure out how they might even begin to understand the world. So Traditionally, this is how robotic systems look like. Before AI became accessible and trendy, robots were built using rule-based logic and finite-state machines. Their behavior was governed by predefined rules, with movements controlled by PID controllers and hard-coded routines and the such. And usually sensor input in traditional robots was more like a simple trigger rather than a source of rich information, if I can say that. A sensor would cross a threshold, let's say, like a distance sensors detecting something closer than 10 centimeters, and the robot would react with predefined actions like, oh, there's an obstacle in front of me. Turn 45 degrees to the right, go forward, turn 45 degrees to the left, and the such. If conditions change, like maybe the lighting in the environment, maybe the surface texture or the object type, the robot probably wouldn't be able to adapt. It would just follow the same script, whether it made sense or not. And because everything was hard-coded, even the tiniest change in the environment usually required a full round of manual tweaking and reprogramming and retuning, and it's horrible. Now, let's be clear, in a structured and predictable environment like an assembly line, this traditional approach of building robots still works very, very well. But once you want a robot to operate autonomously in a dynamic environment, the traditional approach quickly becomes super expensive and too complex to scale. And this is how robots are built now. Instead of relying on strict rule-based logic, modern robots use something called the movement policy at the core of their control system. You can think about it like the robot's playbook. So it's basically a strategy that tells them what to do next based on what it sees and feels. So rather than hard coding every single step, we train a neural network, which is the policy, so that when the robot encounters a situation like an obstacle or an object that it has to pick up, it feeds the sensor data into the policy, which then outputs commands to its motors like turn left, slow down, grip the object. One way of creating this policy is through a method called reinforcement learning, which is based on trial and error. So when the robot does something right, like successfully grabbing an object, it gets a reward. When it fails, no reward. Over time, it learns which actions lead to success and starts choosing them more often. So this used to be done directly on a real robot, but it has proven to be kind of dangerous both for the robot and for the user. So now it is done in a virtual environment where the robot can be cloned millions of times and the learning process can be run in parallel, massively speeding up the process. Point is, once the training is complete, all those experiences get distilled in a compact movement policy model, which is then deployed back onto the real robot. It sounds simple enough, but there's a catch. To train the robot, we need to mathematically define the task we want it to learn. So let's say we want it to pick up an object. In a simulation, we might reward it when the object's center of gravity moves upwards, right? So this indicates that it's been lifted. But here's the twist. The robot might do something silly to get a higher reward, like kicking the object in the orbit, because higher it is on the vertical axis, higher the reward, right? So it tends to do that instead of actually doing the task we intended. So we make the rules more specific, like reward it only if the object is actually in the gripper. And this works great in the simulation. But this is where things get really interesting. In the real world, how does the robot know exactly that it's holding something without seeing it? Like we know that we are holding a cup without looking at it. And taking it further, how would it know what something feels like, what texture it has, or how something smells like? And this is why we believe that robots actually need smart sensing organs just like us. So think about it. Our skin and nose and eyes don't just send raw data to the brain, they process it and sometimes act on it instantly. Like if a mote of dust or something goes flying right at your eye, you usually blink in a reflex act, even before your brain has the chance to consciously figure out that, hey, there was something heading towards my eye. So by giving robotic sensors their own processing power and lightweight machine learning models, they can make fast decisions right at the edge. So this kind of local autonomy is called distributed intelligence, and we believe it's absolutely essential for building robots that truly understand and interact with their world. So this is where this little guy comes into play. And yes, I know he looks silly, but he's part of this concept that we are developing called the Smart Sensor Factory, which is basically a recipe for developing sensor organs for robots. They are fundamentally made out of an MCU unit, a sensor array, and a machine learning model that runs on the edge. And to facilitate the integration with the ROS2 powered robots, we are using micro-ROS to standardize and make the data easily accessible for the ROS powered robots, right? So ROS stands for Robot Operating System, but despite its name, it's not really an operating system like Windows or Linux. Instead, it's more like a set of tools and standards that help you build, connect, and manage the software components of a robot. So imagine trying to build a robot from scratch. It needs to see using cameras and move using motors and sense using sensors and take decisions and then act upon those. And each of these parts need its own code, but they also need to talk to each other and work together in real time. And ROS is the framework for exactly that. Good. So let's take a moment to talk about micro-ROS because it plays a key role in how all these smart sensors come together. So you can think of it as a bridge between the robot's high-level brain and its low-level sensing and actuation systems. It allows the MCU to communicate with the rest of the robot using the same protocols and abstractions as ROS2. It's super tiny, so it fits right on an MCU target. And most importantly, it allows us to reinvent the wheel. It allows us to stop reinventing the wheel and create custom communication firmware for each sensor. You just take this, plug it in your ROS2 powered robot, and you will find it publishes data directly in a ROS node from where you can super easily grab the data and use it in your robotic logic, right? And I know that maybe standardization just sounds like extra work when you are creating an MVP or a proof of concept, but trust me, that once you start scaling the system and you start to integrate tens or hundreds of these guys, standardization is what will actually save your backside. And with that in mind, let's open the box and take a closer look at what's actually inside one of those smart sensors. For this one in particular, at the core of it is actually something called the Zalmotech Feather RA6 M1, which is this, which is a feather board we have built specifically for robotic applications because it uses the RA6 series microcontroller from Renesas. What makes it a great fit for this application is the fact that the RA6 family of microcontrollers is featured on the RA6M5 evaluation kit, which is the only recommended board by the micro-ROS project. And it's quite obvious that it follows the Feather form factor, which I believe is super familiar for everyone at this point, and it has full compatibility with the whole ecosystem of Feather wings, which are basically add-ons for this board. So it really speeds up prototyping. For the sensing part, we choose the ENS160, which is a multi-gas sensor, and it is sensitive to various volatile organic compounds like ethanol, toluene, hydrogen, and some oxidizing gases. And we ended up with this sensor because we tested quite a bunch of them. And this one stood out because it had a very obvious response when exposed to some smells that we might be interested in detecting, like truffles. And finally, the HML model is where the magic happens and where all of this suddenly makes sense. And Edge Impulse offers an amazing functionality called sensor fusion, which allows us to get data from different types of sensors or similar sensors placed in different locations in space and extract information from how those sensors are simultaneously influenced by various phenomena. So for example, in this case, we can classify the footprints of various odors. And you can see here that for this detection, we have employed 3 classes like truffle, room, and coffee. And we have used the single sensor, the one mentioned before. And we ended up with roughly 70% accuracy, which is decent. And from our previous experience, by adding more sensors with other type of sensitivities, the accuracy greatly increases. All of this then gets packaged in a very small edge machine learning model that can run directly on the MCU. And as such, we can run inferences directly on the edge on a very, very small power budget. And the output of this inference is actually the information that gets forwarded to the main processing unit instead of having an endless raw data stream that would lead to that cognitive overload that I was mentioning at the beginning of the presentation. So this is a very short video with the smart nose, if you will, where you can see the LED lighting up when it detects a particular smell. I did not share the ROS2 node output, but it can differentiate between coffee and truffle oil. Right. And finally, just to make my point clear, I want to show you another example of such a smart sensor. And in this case, it's a tactile one. So here in this video, you can see a robotic arm that is looking at objects, counting them, picking them up, and then placing them in a bin. So initially, when using input only from the camera due to changes in the illumination condition or such, the robotic arm would go and try to grab an object, sometimes miss it, but then still do the whole routine of going above the bin, dropping the object, going back, looking for other objects, and being stuck in this loop. And we tried to find a lot of ways to fix this failure of the robot, which is more environmentally based. It was not really something we could offset from the programming. And that's when we decided to create this tactile smart sensor. And basically what we did is that we created a little robotic version of the mechanoreceptors we have in our fingertips. And we have added 2 pressure sensors right on the tips of the gripper, right? So now, when the robot closes its gripper, it doesn't just assume that an object is there, it can actually confirm it, right? So it knows at all times if it's holding something or not. So if there's no pressure feedback, it knows it missed, it goes back in the home position, reevaluates, introduces some offset, tries again until it precisely grabs the object. And then if it finally grabs the objects, that's great. It proceeds to the next step in the task. And just like with the gas sensor, this tactile sensor processes the data right at the edge using a small machine learning model to classify the grip as either successful or not. It then sends just a simple yes or no to the motion policy. And this actually makes the robot much more reliable because it wastes very little time trying to move objects that are not actually gripped in the bin, right? So inside this smart sensor, we also have the RA6M1 featherboard with 2 pressure sensors, an edge pulse sensor fusion model, and micro-ROS to keep everything tidy and make it easy to integrate with ROS2. This being said, thank you for your time. I hope you now also share the same belief with me that if we want to build smarter and safer robots, we must help them better understand the world in which they function, and that this understanding starts at the sensor level. And because when sensors don't just sense, but actually understand, we unlock a whole new generation of robots that are more aware, adaptive, and more human-like in how they perceive and interact with their environment. So thanks again, and I am looking forward to answering any questions you might have regarding the project.